Hello and welcome to this webinar session where we will talk about going from SOLIDWORKS simulation to SIMULIAworks to be able to perform advanced FEA for product development. My name is Sashi Sitambaram and I'm a simulation technical manager and I will be your presenter. At the end of this webinar, I will be sharing my email, so if you have any questions about today's content, please feel free to send that to me directly. So let's start by answering the question, what exactly is SIMULIAworks and how does it differ from SOLIDWORKS simulation? SOLIDWORKS simulation was built primarily for the SOLIDWORKS user to validate designs and drive design changes using simulation results. It offers a great solution for simulation at different levels of complexity and is complementary to the design process because it is fully integrated with SOLIDWORKS. Now, on the other hand, for advanced, high-end, or complex physics simulation, specifically, um, Dassault Systems Simulia has some of the best products in the world, such as Abacus, Tosca, and FE-Safe. So, over the last few years, SolidWorks users, like many of you, have asked us for more simulation capabilities beyond SolidWorks simulation, but not quite as much as what is available within Simulia. So, what we've done is we've taken the SolidWorks and Simulia team, we've come together, and we have created SIMULIAworks, a cloud-based simulation software on the 3D Experience platform that integrates with SolidWorks. So we see SIMULIAworks as an expansion to SolidWorks simulation. So the primary goal of SIMULIAworks is to be able to solve complex physics faster with confidence. And combining that with the 3D Experience platform allows for seamless collaboration. It is a very powerful tool as it uses the Abacus solver, which is by far the best FEA solver in the industry. It is proven, robust, and reliable. Because of its superior ability to handle complex contact conditions, meshing, and material models. It is integrated with SolidWorks and automatically transfers simulation models, features, and materials. And of course, it is cloud-based, making it easy to solve large and complex models with cloud computing and easily share simulation results over the cloud. With SimuliaWorks, you can solve many different types of analysis, such as linear and nonlinear, static, dynamics, and buckling, complex frequencies, modal dynamics, visco and creep studies, thermal and thermal stress, sequential multi-step, which we'll see today, as well as implicit and explicit solvers. So when we talk about SolidWorks simulation or talk about going from SolidWorks simulation to SimuliaWorks, the question is why, when, and how. A reason to migrate to SolidWorks from SolidWorks simulation to SimuliaWorks would be problems with large deformation or strain. Nonlinear problems with advanced contact conditions would be another great reason to migrate over. SimuliaWorks also offers different mesh elements and features to handle complex geometry, whereby SolidWorks simulation only offers one mesh element, which is the tetrahedral mesh. SimuliaWorks also has a much faster solve time for advanced analysis in comparison to SolidWorks simulation. And of course, SimuliaWorks offers capabilities beyond what is available today in SolidWorks simulation. So this answers the why and when. But what about how? To take a look at how to transfer your simulation models from SolidWorks simulation to SimuliaWorks, we'll take a look at today's example. And while we run through this example, we will see not only how to transfer SolidWorks simulation studies directly to SIMULIAworks through the 3D Experience PLM services. We will examine what was automatically transferred, how the mesh as well as the contact conditions are transferred over, how to set up a multi-step analysis in SIMULIAworks, and last but not least, how to view your results and create animations, contour plots, make parts transparent, and things of that nature. So for today's example, we have a plastic syringe. This is typically used to administer liquid medication to infants or animals. So if you have a baby, pets, dogs, cats, you've probably used one of this at some point. So let's go ahead and switch over to SolidWorks. So here you can see the syringe assembly, which consists of three parts: the barrel, the plunger, and the stopper, which is made out of rubber. The way a syringe works is this rubber stopper is compressed, so when the plunger is pulled back, it creates a low pressure area right here, which causes the liquid to be sucked in. Now, if we zoom in to this model right here, we can actually see the stopper is currently interfering with the barrel. So for this analysis, I will need to first compress the stopper to fit into the barrel. And then I would like to pull the plunger along with the stopper while it is under pressure. So for this operation, I would like to validate two sets of results. First, the contact pressure between the stopper and the barrel. Second, to verify the stopper is not overly stressed due to the compression and friction when the plunger is pulled out. So here is an exploded view of what the simulation might end up looking like. All right, so let's go ahead and switch over to the simulation view. So you can see that I'm only using a quarter of the assembly because it is a circular symmetry. Because of the nonlinear nature of the rubber stopper, we will need to solve this as a nonlinear analysis. So I've already started to set up the analysis. So let's go over what I've done so far. So for the barrel and plunger, I've actually set this up with a general PBT plastic material. Now, the reason why I've chosen this material from the SOLIDWORKS database is because I don't foresee, or the reason why I've chosen a linear material here is because I don't foresee these two plastic parts, deforming too much. So I'm able to just use a linear material model here. However, for the rubber, due to the compression and then the 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 contact friction, I do need to set this up as a nonlinear material model. So here I've actually created a custom material rubber using a hyperelastic Mooney-Rivlin model, where I've inputted the Mooney-Rivlin constants here, the first and second constants. Let me go ahead and close this. So as part of this analysis, I've also set up two contact conditions to ensure no penetration between the stopper and the barrel, and also between the stopper and the plunger. Um, in hindsight, if my intention was to transfer the analysis over to SIMULIAworks all along, I actually would not need to set up these contact conditions because SIMULIAworks by default treats every component as no penetration because of its superior contact feature. So you can see here to set up this contact condition, I actually had to select quite a bit of faces on the stopper and then quite a bit of faces on the plunger. So not having to do this is actually a huge time saver. Now for the fixtures, I have a 15 millimeter translation on the back face of the plunger to simulate it being pulled out. I also have a roller. I have roller slider boundary conditions set on all the symmetry faces. Which is a known simulation method when applying a cyclic symmetry condition manually. Lastly, I also have a fixed condition right here on the barrel to ensure that it does not move. So, while setting up this analysis in SolidWorks simulation, I've come to realize that this might be a challenging simulation to solve due to the multi-step analysis required. First, the compression of the rubber, then the plunger being pulled out. There is also a considerable amount of contact being solved for this analysis when the plunger is being pulled out between the plunger and the stopper and the barrel. So for these reasons, I think it would be best to transfer this model over to SIMULIAworks. To do that, we will open up the 3D Experience PLM services, which is right here. And to turn on your 3D Experience PLM services, you can actually just go into your Add-ins tab, and it will reside right here. So just hit this check mark to activate this add-in, say OK, and this will show up on these tabs right here. So before I transfer over my model into 3D Experience, I need to make sure that I have the latest version saved within the PLM services. So let me go ahead and do that here. So I'll first need to reserve the model, and then I will save the model. So now that the model is saved, I will unreserve it. So now by clicking this icon right here, which says create structural simulation, it will start to transfer this SolidWorks simulation study to the 3D Experience simulation. So now it says your simulation has been created and is ready to use in 3D Experience. Open it in 3D Experience, and I'll go ahead and say yes. So now the model will transfer over to the 3D Experience platform, and it will automatically start up, as you can see here. So this will typically take a few minutes. Okay, so now the 3D Experience platform has automatically opened up, and right away it brings up this window where it is asking to initialize the simulation and transfer the simulation parameters over from SolidWorks simulation. I'm going to go ahead and say OK right here. And right now, what's happening is that it's actually taking all the parameters from SolidWorks simulation and transferring it over into the correct parameters for SIMULIAworks. So you can see that the transfer is done. And right away, we get this simulation status window, which shows us exactly what was transferred over. So if you take a look here, the materials, both the material from the SolidWorks database, the PBT, was transferred over, as well as the custom material, rubber. And it was transferred over as a hyperelastic model. We can see here that the connections were not transferred over. As I had mentioned earlier, um, SimuliaWorks handles its contact conditions in a much superior method than what is available in SolidWorks simulation. So it actually disregards the contact conditions from SolidWorks simulation and automatically creates the advanced contact conditions in SimuliaWorks, which we'll see in a second here. Um, it has also transferred over all the contact conditions all the fixtures, and all the roller sliders are in with the green check mark. We do have an information icon for the reference geometry, and we'll take a look at why that is here in a second. And if you have some mesh conditions set up within your SolidWorks simulation model, whether it is global mesh or localized mesh, all of that would also would be transferred over. So I'm going to go ahead and close this. Now, the easiest way to view what was transferred over and how it was transferred over from SolidWorks Simulation to SimuliaWorks is to go into your Feature Manager. So I'm going to click on Feature Manager here. And the Feature Manager shows us basically everything that we just saw. So the fixed condition is right here. The roller sliders are right here. Now let's just take a look at that reference geometry, that applied translation, to pull the plunger out by 15 millimeters. Let's see why we had that information icon. And the reason for that is because instead of transferring that over as a boundary condition or a restraint, it has actually just transferred it over as a load, as an applied load. So the way SimuliaWorks handles translation, it classified as under the load category as opposed to the restrained category, which is essentially the same thing. So just to verify how that looks, so you can actually just double click on that. You can see that the selected face, the direction of the applied translation, the 15 millimeters, the direction, it's in the Z direction. So everything looks good here. So I will just hit OK and go ahead and exit out of this feature manager. So I do want to make a few slight changes to this analysis before I go ahead and run. And the first thing I would like to do is actually make a change to the mesh. So to do that, I'm actually just going to switch this over into the mesh model right here. And I'll click on the mesh part manager. So here I can actually see all the three components. And what I'll do first is I'm going to actually make a change to the stopper. So I will actually just double click on the stopper right here. So this brings up the window where I can change all the stopper information. Now I do have a lot going on in the model right now, so I'm just going to go ahead and just hide all of these restraints arrows. So I can just do that by right clicking scenario and saying hide. And I'm going to set this mesh size here for the stopper to 1 millimeter and the absolute sag to 0.1. Now I also want to set up some localized meshing on the faces that are touching the barrel. And to do that, I can actually hide the other components, and all you need to do is just hover over the other components and just hit F7 on your keyboard, and that just hides those components right away. So to add those localized mesh, I'm just actually going to click on this icon right here, which says local mesh size. I can select on this face and this face, and I'm going to set that mesh size to 0.3 millimeters and the absolute sag to 0.03. I'll say OK. Oops. I think and set that to 0.03 and say OK. And now I can go ahead and just hit mesh, and the pod is now meshed. So I'm going to go ahead and say OK here. And now my status for this has changed to OK. So the next mesh I would like to change is the plunger. So to do that, I'm actually just going to bring all my components back, and I can just hit F8 on my keyboard, and it will bring all my components right back. So to change the plunger, I'm going to double click on the plunger component, and I'm actually going to change the name. So the component name actually did not transfer over for this specific component. So I can actually do that here manually. I can just say plunger, and for the mesh size, I will do 2 millimeters and 0.02 millimeters for the sag. And I'm also going to set some local specification, local mesh. So again, what I'll do here is I will um, select F7 on those two components. And specifically the faces that are touching the stopper. So I'll click on this. I'll select on this face, this face, this face, and this face, and this face. And here I will change this size, this local mesh size to 0.2, and the absolute sag to 0.02, and I'll say OK. And I'll hit mesh and OK. All right. So the last component that I need um, to mesh is the barrel. So again, I'll just double click this. Again, I'll change that name, barrel. I'm actually not going to do any localized meshing for the barrel, so I'm just going to put a 1.75 mesh here, 0.075 for the, sorry, 0.175 millimeters for the absolute sag, and just hit mesh. And I do get a warning here, and perhaps we just need to make the sag a little bit smaller. And now everything seems to work fine. So in case you're wondering what this sag is, this is essentially um, the maximum distance between the mesh element and the solid body. Um, and this usually has to be around 10% or less. So you can see that, when I got that warning message just now, I just kind of dropped it a little bit more, and everything seems to be okay and working fine now. So I'll go ahead and hit OK here. Um, Now the next thing I need to do, and I can actually just right click this mesh and hit hide, and that hides the mesh. So the next thing I need to do here is to set up a multi-step procedure to incorporate the interference fit right here. To add a new step to the analysis, so you can see that as part of the transfer, there is already one static step, but to add an additional step, all you need to do is just navigate to scenario, go into procedure, and then select on the step, the intended step. So you can see here that we do have many different types of steps available. If you click on a static step, it will create that next step for you. So to view or to see this see this setup for this analysis, we're going to set up 3 separate steps. Let me go ahead and open up a completed analysis. So I'm actually just going to use my search window up here to easily navigate um, the simulation that I've already completed. And I'll hit open right here. So this is the completed analysis. So again, I'm just going to go ahead and just hide the scenario and the mesh. And for the steps, what we have here is three separate steps. So the first step, if I double click, we can see it's called an interference frictionless. So when we are trying to apply the interference, we actually want to remove any type of friction between the surfaces. So um, in this first step, you can see that all I have is just a general contact um, between all the surfaces, and what that is um, just a contact condition where all surfaces, all components are by default no penetration, or the equivalent of no penetration to SolidWorks simulation. So this actually came in as part of um, the transfer from SolidWorks simulation. So I'll hit OK here. So the second step is where I start to apply the friction. So you can see here, it's pretty much this in terms of the step, everything here is pretty much the same. But the one difference I have here is I've actually added what we call a tangential behavior override. So what this is I'm actually overriding the initial contact in my first step to add the friction here. So you can see that I have a friction coefficient here of 0.1. So if you take a look in terms of comparing the first step and the second step, the first step has the general contact, and the general contact will be will um, will work throughout all three steps, because anything that you set in the first step will automatically translate to the second and third step. But what I have here additionally in the second step is to override um, the contact in the first step to add that friction. And then for my third step, it is to essentially simulate that plunger being pulled out. So uh, everything is the same. The only difference here is that in the third step, I have this reference geometry that applied load is turned on, versus in that here it is considered 0. All right, so now that I have all my steps in place, I can actually run the analysis. So let's take a look at our results. So I'll go ahead and select on results here. So right now what it's doing is it is just collecting all the results. I've actually pre-ran this analysis, obviously, for the sake of time for this webinar. So we can actually just jump right into the results. So what we're looking at here is the stress. And because SIMULIAworks is by nature a nonlinear solver, and it solves analysis in an iterative manner, so you can actually view how the analysis or the results at every iteration. So we can actually just go right to the last iteration right here to view the stress on the part. And as you hover over your model, you can actually see what that stress is in that area. So it actually gives you quite a in-depth look into your simulation results. Um, So I can also very easily switch over my results to other plots that I have here. So I also have a contact pressure plot, and we can actually view what the contact pressure is here for this component. Now to get the view on the other side, I probably want to make this component transparent. So to do that, again, I can just hover over the part and just hit F7, and you can see that it actually made that barrel transparent. So I can actually see and hover over the stopper to see exactly what the stress is, or the contact pressure is on that stopper. So in addition to this, I can also animate the results. So to do that, I can actually just hit on play animation, and you can see how that plunger looks. And hey, it looks a lot like that explode animation from before. So you can see actually there's a slight delay in the start of that animation, is because that stopper is being compressed for the first for the first step, and then the second step, the friction is changing, and then the third step is when that plunger is actually starting to move. So to view this component in 3D, sorry, in a full view as opposed to a quarter model, we can do that by navigating into the display tab right here. I'm going to select on the results option. I'm going to select on model symmetry. I'll say check on model symmetry right here, and I'll hit close, and now you can actually see the model in a 3D view. And I can also animate this just like before. And just like SolidWorks simulation, you can capture your animation, you can capture all your results. There are all different tools here to help you do that. All right, so that completes the presentation within SIMULIAworks today. So let's go ahead and switch back to my slides. So to summarize, the 3D experience on cloud simulation, easy to use, smart applications to remove guesswork for optimized product design. It is high-end technology to create realistic simulation in a unified environment. It is integrated. Not only you can transfer over SolidWorks models and SolidWorks simulation models, you can also open up step files, IGES files, SolidWorks files directly within the SIMULIAworks environment and set up your analysis natively within SIMULIAworks. So let's say if you don't have SolidWorks simulation today, that's not a problem. You can start off all your analysis right within SIMULIAworks. The collaborative aspect is great, being that it is on the 3D Experience platform. Anyone that has access to the 3D Experience platform, you'll be able to easily share all of your results. You can share the animation, you can share cut plots very easily, you can share contour plots. Scalability. Uh, SIMULIAworks is built not just for high-end simulation users, but simulation users of at all levels. So from your designer level, engineering, mechanical engineering, mid-level engineers, engineering managers, all the way up to FEA analysts. In terms of productivity, there's really no comparison, especially when you have an on-cloud solution like this. And of course, with the on-cloud solution, it minimizes hardware and software costs. As many of you know, to be able to run high-end simulation, you need to invest in a lot of hardware. With the on-cloud solution, now that kind of goes out the door, and that's quite a bit of savings for you. So what's next? So to learn more about everything that you saw today, you can actually just hop on to www.solidworks.com/simuliaworks. On that website, you'll find videos, white papers, blogs, all sorts of information, customer stories on how they are using this tool today to generate great results and how it's changed their engineering process. You can also go to my.solidworks.com, and if you search for Simulia Structural, you will actually be able to view videos. You can also access blogs, information, up-to-date information on everything SimuliaWorks. You can also reach out to your SolidWorks VAR. So all of our SolidWorks VARs today have access to this. So if you would like to see a demo, perhaps even give this product a try, whether it's a hands-on test drive, get in touch with your SolidWorks VAR to learn more about all the capabilities of SimuliaWorks. So to wrap this up, if you have any questions on today's webinar, this is my email, sashi.sitambaram@3ds.com. Please feel free to send me all your questions, and I look forward to hearing from you. Again, thank you very much for joining me on today's webinar. I hope you were able to learn something new, and I will catch you on the next webinar session. Thank you all, and have a great day.